structural masonry and fiber reinforced polymers. Here is the program description and our learning objectives. You will also receive 1 PDH and 1 AIALU for those architects. Our provider statement as required. All the certificates and evaluations will come from myself, so be looking for those after the program. We do have giveaways today of the TMS 402-602 2022, and the handsome fellow is our great Masonry Structural Coalition, Greg Bryant. We're not giving him away. I don't think his wife would appreciate that, but we are giving a nice jacket from the Mason Contractors Association. They were chartered 1896, and they are one of the area's oldest construction industry trades. So place your business card or just your name in the box that's going to be coming around shortly. And our sponsor today is Ranieri Building Materials. They're a family-owned company located in St. Louis, Missouri, specializing in ready-mix concrete, masonry, plaster materials, and construction tools. Ranieri Building Materials has been providing its customers with quality products and service now for over 6 decades. Thank you. And is Nick Ranieri or Ryan Ranieri here? No, but we thank them very much for the refreshments. Today's speakers, Dr. John J. Myers. Dr. John Myers is a professor of structural engineering in the Department of Civil, Architectural, and Environmental Engineering at Missouri University of Science and Technology, and is director of the Missouri Center for Transportation Innovation. He served as Associate Dean for Academic Affairs in the College of Engineering and Computing from 2015 to 2020. Dr. Myers has been a member of the Missouri S&T faculty since spring of 1999. He holds a bachelor's degree in architectural engineering from, sorry, my structural brick almost gave out on me, the Pennsylvania State University. He previously served as a college acting vice provost and dean. Dr. Myers has researched high-performance materials for the past 30 years in relationship to structural engineering applications. Relative to today's presentation, Dr. Myers is current secretary for ACI Committee 440 on fiber reinforced polymers and assists in an advanced role to the TMS Appendix D task group and a consulting member of PCI's FRP Composites Committee. So please welcome Dr. John Myers.
Thank you. All right. Thank you so much. The microphone's working, which is good. And I love to start off with just kind of a little survey here. How many engineers do we have here today? Okay. Any architects? All right, good, good. We welcome architects too, right? Has there been anybody out here that is familiar or used FRP products in the past? Okay, so today's introduction and presentation, we're going to talk about the use of fiber reinforced polymers and sort of how that compares and contrasts to using mild steel, for example, to reinforce masonry. And my presentation, before I get into that, I want to just do a little plug for the university. We've been around since 1870, and 2 of our first 3 graduates going back to 1870 were actually in civil engineering. Some of you may know us as Missouri School of Mines and Metallurgy, University of Missouri Rolla, or now Missouri S&T. So I'm going to refer to Rolla a lot. And we're just down Interstate 44. You know, of course, St. Pat's, we've got a little event coming up in a few weeks. St. Pat's Parade, that's our big event in Rolla, if you're around. But again, we're the oldest STEM university west of the Mississippi River. And fairly recently, thanks to one of our civil engineering alumni, Mr. and Mrs. Fred Kummer, who is from the St. Louis area, gave over 300 million to the university. So it's really been transformational. And we have a lot of new facilities coming down on campus if you haven't been there. I know we have at least a few alumni from Rolla. Awesome, awesome. Good to see all of you. And one of our biggest additions, thanks to support from Clayco up here in St. Louis, has been the Advanced Construction Materials Laboratory. It's really the top facility in the country now. And that added on to our structural engineering lab here. We really have outstanding facilities and capabilities. Even though we don't have Division I sports, we've got a great academic program. And another thing I just wanted to hit on is we actually have 17 different undergraduate degrees in our college in engineering. And essentially, that's the most of any university in the United States. And also, most of our students are in engineering. So usually it's about 80% of our students in engineering, and specifically that makes us usually top 20 producer of engineers here in the United States. So, you know, if you do have family members, relatives, friends that are thinking about it, come check us out. It's worth the hour-and-a-half drive to take a look at what we've got. One of my roles, I've done a lot of different things over the 25 years I've been at Missouri S&T, but I'm currently the director for our statewide transportation center, and it's actually the University of Missouri System Center. So we work with the faculty not only in Rolla, but also at Columbia, at Mizzou, UMKC, and also up here at UMSL. And it's really neat. One of the big things that you probably have heard of is the widening of Interstate 70 all the way from St. Louis to Kansas City, and that's going to give us a lot of opportunity to hopefully have a lot of innovation in the bridge replacements and some of the pavement systems that go along there. A little outside of masonry, granted, but wanted you all to be aware of that. Today's learning objectives, I'm not going to read them. Margie mentioned some of those, but they're also in your packet for you to study. But basically, we're going to learn more about GFRP and also the new Appendix D. And then I also wanted to pick a couple of research topics. So my presentation is separated into a part 1 and a part 2 that we'll cover. And so part 1 is going to talk about the new Appendix D and TMS 402-602. And I want to acknowledge Heather at Colby Company. She's very involved in the task group working on this Appendix D. And she did give me some of the content for this part of my presentation. So up front, I really want to thank Heather for giving me some of the material in this section of my presentation. GFRP bars date back more than 25 years ago. When I started at Rolla in the late 90s, research was already taken off on how we can use these non-metallic materials in structural engineering applications. And in the early 2000s, actually as early as about 2001, at Missouri S&T, Tony Nanny and some of us at the university did some of the first research on masonry using both FRP for repair as well as for grouted cells as reinforced masonry with GFRP. So even though it's been like 20 years, now we finally got a section in the TMS standard. Where do you want to use GFRP? You know, a lot of times if you have issues with electromagnetic equipment, MRI equipment in health facilities building, it's a good application to do it, as well as in areas where you're worried about corrosion of steel in severe environments. Other applications, GFRP has a very low mass. So when you're doing seismic retrofits or repairs, it's a very high strength material with low weight, low mass, also very good for seismic type repairs. I'm going to go through before we jump into the Appendix D and talk a little bit about ACI, ASTM, AASHTO, and the Masonry Society documents. So all the use of FRP really started back in the 90s in ACI. So the application was, how can I use this as a reinforced concrete material? At the same time, in ACI, we were developing ASTM standards. So if you're going to use a new material in construction, you got to have standards to test it, standards for conformance of the material. And so you can see here ACI started, this is the most recent building code for GFRP in reinforced concrete. And this is code mandate. So if you use this standard as a structural engineer, we're protected under that standard and guideline. But we also develop specifications for construction and also ASTM standards. Here's one of the newest construction specifications. And at ACI, we also develop guidelines on durability. So if you want to evaluate a new composite product and estimate its service life, understand how it is affected by weathering, there's guidelines and standards there. And so I always like to say, you know, you need the 3 legs of the stool. If you don't have the 3 legs of the stool, what can happen? You know, it can topple over, but it's the material spec, the design code, and the construction spec. So even though some of these aren't necessarily falling underneath TMS, these documents are out there at ASTM, ACI, and so forth to help us as designers. Following the development from the late 90s up until today at ACI, on the bridge side, some of the first applications was 2009. Now, what you see in the images here are more use in bridge decks. And we're going to talk about why some components are better use of FRP than long-spanning elements where deflection or serviceability is an issue. But you can see here 2018, and it's really a good place to use GFRP in decks, for example, because they're not necessarily a collector element of loads. So now that brings us to TMS and masonry. And again, we're going to be talking about Appendix D in the new standard that's out there. And we'll look at one example in today's presentation, but your packet also has a second example in the back of it for you to take with you that we just don't have the time to get into today. All right, GFRP. I think I brought a sample with me. I'll pass this around a little bit if you've never seen it. Very lightweight material compared to steel. Basically, if I think of concrete, concrete is made up of what? Coarse aggregate, right? Fine aggregate, Portland cement are the basic building blocks, and potable water, right? In concrete, we get the stiffness from what? The aggregates, right? And the paste, the Portland cement and the sand or the fine aggregate, is the glue that holds the aggregate together. And a composite material like this is very much the same. It's got the fibers in it that carry the load, provide the stiffness, in this case glass, and then there's an adhesive, in this case we call it a resin, that is the glue that can transfer the load between the fibers. So if I use the analogy of concrete, these composites are just the same. One difference here is anisotropic. Okay, sounds like a fancy word. It just means that the properties of the material are not the same in all the directions. So if the fiber is running vertically, that's going to have one stiffness and one tensile strength, for example, in that direction. But if I cut it perpendicular to the direction of the fibers, it's going to have much different properties. So if I take a mild steel bar, right, we call that what kind of material? Homogeneous. So if I cut in this axis, this axis, this axis, mild steel is going to have the same stiffness and the same properties, right? So one thing we need to learn about the use of GFRP is it has different properties in different directions. Okay. When it's manufactured, this schematic shows how it's manufactured. And again, up here you can sort of see a schematic of the actual fiber and the resin. There's different types of resins. There's polyester resin, that's an older generation. Now there's vinyl ester, which is a better product, a better glue or adhesive that's more durable. When it comes to producing it, again, you have the spools of the continuous fiber. You get to a stage where you do some surface treatment. In this image here, you can see A through F. There's different types of treatments I can put on this. Some are just a sand coating. You can see some have some helically type of windings on it. But if you were to guess, why do we care about the surface treatments to the bar or the product? That gives us better bond, whether it's concrete or whether it's grout in a masonry cell. So it is important in terms of the surface treatment to the reinforcing material. We know it's non-corrosive, it's thermally neutral, non-conductive, it's lightweight, like I said earlier. And of course, if I'm at a job site, it's a lot easier to move around because it's a much lighter weight material. So when we talk about Appendix D and its scope, first I'm going to talk about right now what it is included in the document, and then we'll look at what's not included. And the path in terms of what's in the TMS document and design standard is very similar to ACI. As we went along over the last 20 years, each time we developed a new version of it, we added newer content to it to help us as design engineers. Right now, this is an Appendix D, but I see down the road that this will be integrated into the main section of the standard. But again, G standing for GFRP. There's different types of FRP. There's carbon, there's basalt, there's other bars out there. This document right now just looks at this use of glass. And I'm going to talk about why glass is a really good material for masonry, because it's very compatible to be used in masonry rather than a carbon. If you hear the word carbon, what maybe pops into your mind? A company that's a little north of us, Boeing, right? There's a lot of carbon fiber in the aviation industry. It's much more expensive. It's got much higher tensile capacity, as high as 300 KSI, compared to maybe 100 KSI or 90 KSI in terms of the tensile capacity of GFRP. But again, you can see that this does include reinforced walls and lintels, non-bearing walls, non-participating element. And this image here is kind of whether it's a lintel or whether it's a wall element. This is a big addition, so now you can have the option of using GFRP compared to maybe mild steel as an alternate. It also includes guidelines on how to determine the development length, so how far we need to anchor this in order to develop the tensile capacity of the reinforcing material. I showed an image that I put together on splices here, hooks and bends, deflections, and creep rupture that we'll talk about. So all these are covered in the Appendix D section. Now, right now, because this is a linear elastic material, there's not as much has been developed on seismic requirements. And I'll go back to when I was working on my PhD at Texas back in the early to late 1990s. We were working on high-strength concrete. Everybody was concerned, well, high-strength concrete, if I put it under compression, it's very explosive when it fails. It's not a very ductile material. All very true, but over time, we learn more and more about how we can reinforce it to even use higher strength concrete to give us ductile behavior. And now we have a thing called what? UHPC, that is a very ductile type material. So even though right now there's not a lot of seismic guidelines on using these materials because they are linear elastic and they don't necessarily have a yield plateau like mild steel reinforcement, you know, people are diligently working on this, and I suspect down the road for seismic applications we will develop good connections in order to do an entire masonry structure out of FRP, even in a seismic area. But there are some guidelines on that. Now, what does TMS 402 and 602 not include in terms of the appendix? Right now, bearing walls, shear walls, columns, and so forth. And again, it's not that the knowledge is not necessarily out there. It's just incrementally taking the steps in terms of building up the document to address these. The other thing that is not covered is externally bonded. So cosmetically, maybe this isn't the most attractive thing to do to a masonry wall. We all agree with that, especially our architects in the house here. But there are techniques to strengthen masonry walls, and this is called a near surface mounting technique, where you slot the bed joint and you can put it in there either with cementitious or with a epoxy material to get additional strength. A lot of times this might be used on unreinforced masonry walls, or you can use laminates or sheets that we call here. Now, this currently is not in TMS documents, but we developed, and I'm on this subcommittee at ACI as well, ACI 447 covers if you want to repair masonry for whatever reason. Maybe it's a new classification, maybe it's an upgrade in loading needs. You can go to this document and it tells us how to do that for repair. There's a property called the glass transition temperature. So we use this fancy term GFRP, but what is this? It's a plastic, right? We don't like to call it a plastic because some people think plastic is an inferior material, but this is a design material for our needs. But there is a property called the glass transition temperature. So if the temperature gets excessively high, that resin or adhesive or glue can soften, and that kind of gets above this transition region here. And the glass transition temperature is dependent on the bar, the materials that go into the bar, but you can see usually it's between 212 to 250 degrees. There's a new fiber, basalt fiber, that does a little bit better with higher temperatures. But if I go to the ASTM, basically if you're at this minimum glass transition temperature here, that's basically a service temperature of 185, okay? Now, someone may say, well, hey, what if there's a fire and this is in a building? Well, there's ways to improve the fire rating of components using FRP. If I look on the right, I see mild steel. From a bond perspective, what do we get out of the mild steel? We get friction, helps us with the bond, and the other is the mechanical bearing, right? These actual lugs. One difference from a perspective of developing and the bond or splicing the bar is that the coating system we use on these is a little bit different. So usually the development length, the splice length of these products are going to be a little bit longer than mild steel, because here you get the frictional restraint as well as the mechanical bearing, right? You remember your reinforced concrete classes, right? But there's different types of coatings that are done. In fact, there's a bar manufactured in Australia where they laser etch it. So they actually laser the cross section so they get a little bit more bearing, but then they sort of waste material by reducing the cross-sectional area when they laser etch it or they groove it a little bit. Okay. Here's a comparison of some early research where the blue line is a steel reinforced wall, the black line is the FRP reinforced wall, the experimental results, and this was done by Gustavo Tuleman, who's one of our graduates down at Missouri S&T. But here basically what do you see? You can get equal or higher strength out of the FRP reinforced wall, but you do get more displacement because this material is not as stiff as mild steel, okay? But you'll see the green line is the service level load we need to get to. And, you know, this was the model, this was the actual performance here. So you have an idea on that. When this material is used, whether it's concrete or whether it's masonry, the two failure modes are going to be either what? Crushing of the masonry unit, right? Or it's going to be, in this case, rupture of the bar. If I was using mild steel, what are my two failure modes? Crushing of the masonry or steel yielding, right? And in the middle of those two, what is that? The balance condition. So there's some middle point in between the two where the masonry can crush and the bar can rupture simultaneously. And the reason we're interested in the failure mode is because that is going to affect what resistance factors we use, safety factors we use in design. Now, if I was designing a masonry wall with steel in it, and I asked any of the structural engineers in here, what failure mode would you actually prefer? Steel yielding or masonry crushing? And you would say, steel yielding. Okay, good answer, A+. And what's a benefit of using a section that is tension controlled if I'm using steel? Think about the phi factor. Is the phi factor higher in the code when I'm using steel and it yields versus masonry crushing? Shake your head, yes, it's higher. It's 0.9, right? So there's an economic advantage to also having steel yielding. In this case, when I look at these two failure modes here, which one would you probably want to avoid? Rupture. So actually, we have to think a little bit differently when we design with FRP, that we actually prefer a masonry crushing as opposed to actual rupture of the bar. Okay? Now, that sounds counterintuitive, but it's actually better because there's less risk of an actual structural failure in the system. However, the factors that we use in design really protect us from ultimately a crushing failure. Here's two examples. On the right, you can see a wall under load. No, I'm sorry. On the left, on your left, you can see the wall under load. You can see these materials can really displace quite a bit. Now, this is above the cracking moment, so you do have obviously some damage in it. But once you let go of the load, it will actually, because it's a linear elastic material, you'll have some deterioration or cracking in the wall system or the beam system, whatever you're designing, but it will kind of rebound like a rubber band back into its undeformed shape with some displacement related damage. And this sort of shows us a plot of the moment versus the area of the reinforcement. If I increase the area of the reinforcement here, the more reinforcement I put in, just like an over-reinforced member, I'm going to push it towards a compression failure, right? Think of a concrete beam, think of a masonry lintel. If I have a low amount of reinforcement, if it were steel, the steel would be expected to yield before the material crushes. But in this case, we're going to actually rupture the material. Okay? And then in the middle, there's a transition. Right here, the line between tension controlled and compression controlled is that balanced scenario where both would occur simultaneously. And here again, you can see steel in the very fine dashed line. You can see GFRP. Again, there's no problem, you know, capacity-wise, trying to generate higher levels of load. However, since the failure modes are a little bit different, rupture of the bar, we have different resistance factors in this document. So actually, if I have tension control where the FRP is going to rupture, the phi factor is 0.55. And you can see what the resistance factor plot looks like here. And on the bottom, if it's compression controlled, it's 0.75. Now, if I want to get more efficient use of my material, as a designer, you want to use which type of failure mode in general? In this case, I'd like to use compression control because it's 0.75. If we flip this around and we have a masonry system with steel in it, this value here is going to be 0.9 for tension controlled and 0.75 for compression controlled. And so actually, if I have a plot here, you know, it's going to go across at 0.75, it's going to transition, and it's going to be 0.9 up here if it's steel. So I'm just trying to contrast the difference between using FRP and steel. But, you know, from an efficiency standpoint, I'd rather apply 0.75 to my moment calculation rather than 0.55. So we actually are trying to push the designers to have compression controlled rather than actual loss of your tensile reinforcement, if that makes sense. Here, you know, here are the mechanics involved. On the top is the strain, on the bottom is the stress, on the left is the compression control where we have masonry crushing, on the right is GFRP rupture. I'll point out a couple of things here. One thing you notice is the location of neutral axis. When we have GFRP rupture, it's much higher in the element, as you can see here, the beam element. And it's much lower in the element when we have masonry crushing driving this up to our maximum usable strain in the masonry for crushing, okay? Now, when it's on the tension controlled side, what happens? My bar ruptures. When it's compression controlled and masonry crushing, I'm not at the tension capacity to rupture this bar, right? So we need an equation to estimate what the stress is in the bar if we have a masonry crushing controlled failure. And that's what this expression is here. We're not going to get down into the nuts and bolts of this, but you do have some examples. This estimates what the actual stress is in the bar when we have masonry crushing. There is also an estimate of where the neutral axis is under the balance condition, which is this expression that helps us to estimate, again, where that neutral axis is located when we have GFRP ruptured or tension controlled, okay? So two different values for the stress in the bar at rupture versus when we have masonry crushing. And in this document here, you can see there's the C sub B, the neutral axis, when we have rupture of the FRP. I was just going to point out here that we estimate the stress block on the compression side by 0.8 of that C sub B value for the balance condition, and that's how we estimate what it is. Realize that the shape of the stress block and the strain block is a little bit different for masonry crushing versus rupture. When we look at the materials, another thing I want to point out is if you order a grade 60 mild steel bar, what's your guaranteed yield strength? 60 KSI, right? Ultimate's probably going to be 75 to 79, somewhere in there. These bars all vary. So there's different manufacturers, and you might say, well, why do they vary? Well, that's because when I make this bar, just like I'm batching concrete, one ready-mix plant may put more Portland cement in than the other ready-mix plant. So the properties of the concrete are going to be different. The ratio of the fiber to the resin or the adhesive, there's a requirement that you have to have 70% fiber as a minimum. But different manufacturers have different sizings of the fiber, so all the products are a little bit different. So when we design, you know, we might have to make some assumptions on the properties of the bar. And there's not lots and lots of rebar manufacturers. There's Owens Corning, there's V-Rod, there's several ones. But it's important to know that you need to understand what the manufacturer's properties are that you're going to be using, or your best estimate that you can come back and tweak later as the designer, maybe in a spreadsheet. The other thing is that the bar size affects it. Smaller bar diameters, because of the sizing of the fibers and the ratio of the fiber content to the resin, affect it. So smaller bar diameters generally always have higher tensile capacity than, for example, a number 8 bar, a number 10 bar. The larger the diameter of the bar, usually the lower the tensile capacity because of the surface area to volume and some of the logistics of the content of them. But here you can see that there's ASTM. It gives some minimum requirements. So you can always design from the minimums, but of course, if you want more effective use of the material, you want to know exactly what you're working with. One of the things we apply to GFRP is called the C sub E, or the environmental reduction factor. So, you know, this is always kind of odd for people, but if I have an outdoor structure and it has steel in it, at some point, what's eventually going to happen to the steel? It gets oxygen, right? It gets moisture. What's going to happen to the steel? It's going to corrode eventually, right? Now, we never put a penalty on steel because it might corrode one day, partly because we know that it has strain hardening. We get extra capacity out of it, and we have load factors and all these other things. Since this is a linear elastic material, we apply an environmental reduction factor, and we use 80% and 70% depending on its location. And there's 3 things that these bars are affected by. One is temperature, right? We know a little bit about excessive temperature, but temperature can affect it. Moisture can affect mainly the resin, not the fiber so much, the resin mainly. And the other thing that can affect it, I said moisture, temperature, is stress, so sustained stress. The other thing is we have a bar bend factor K sub B. So if I manufacture this bar and I want to put a bend in the bar, the properties around the bend are a little bit different than in the straight portion of the bar. So if we have something where the bend properties are critical, we actually have a factor that takes into account the fact that when we manufacture and bend this bar, the fibers may congregate to one side of the bar. Imagine a bend. It's bent using, I forget what they're called, using a, well, mandrel. Thank you very much. They're bent using a mandrel, and so some of the fibers will congregate. They won't be evenly distributed. So that's where this bend factor comes into play here. Again, for environment, moisture, temperature, sustained stress, I always liken this to, again, steel is going to corrode, so you know all materials eventually deteriorate at some point, whether it's slow or fast. And this takes into account the bend, as we talked about. So one of the things is we get the manufacturer's properties here, F sub FU. The students always laugh when I say F sub FU, you know, in class, but that's the ultimate capacity, tensile capacity of the bar. We multiply it times the exposure it's in, and then if there's a bend in the bar, we would apply the bend, whether it's, if there's no bend, it's 1.0. We apply that to both stress and strain. So it's kind of like a knockdown factor. Think of it like another resistance factor, essentially, right? And again, just keep that in mind. That's something that we're not used to regularly doing. We have the phi factor we talked about. We apply that to the nominal. And of course, we make sure it can carry the loads, the ultimate factored loads we're designing for. If it's controlled by masonry, this is our equation, our moment, our area of reinforcement times the stress in the bar from that earlier equation I showed you when we have a compression controlled times its moment arm. If it's GFRP reinforcement, then we have the ultimate capacity for design. That was in the last slide, times the cross-sectional area per foot if it's a wall, something like that, times its moment arm. And again, there we're estimating what the depth of the Whitney stress block effectively is, divided by 2. Okay? And this just sort of shows what we were looking at earlier. And keep in mind that we have 0.8 times F prime M. And there's also a factor that comes in here, whether the grout is not horizontal or whether it's continuous horizontal, because that gives you more capacity in the element in the section. For shear, actually in shear right now in the TMS document, we ignore it. So if this were concrete, we would have V of C from the concrete, and we would add V of F from the stirrup or fiber that's made out of FRP. We're taking a conservative approach in this document, and we're saying, hey, there's no contribution from the GFRP, even though really there is some contribution in terms of shear resistance. But for now, it's silent and it's ignored. But some of these other relationships are very similar to what you might see previously. Creep rupture. If I take this bar and I keep a sustained load on it, over time, if that sustained load is too high, it can result in an unintended rupture of the bar. So a lot of our materials are creep sensitive that we use in different applications, and this is one of them. Now remember, when I say sustained loads, right, I'm talking about, you know, effectively like the live loads that are involved. Wind load, if it's a wall, those sorts of things. But we do need to make sure that it's less than 30%, okay? So that's another consideration, and you see my note up there that higher levels can cause an unanticipated rupture of the material. So let's take a look at an example, and I better pick up the pace a little bit. But here's an example of an 8-inch CMU wall. It's got the masonry characteristics, the maximum usable strain in masonry, and location of the reinforcement, the amount of the reinforcement. These values for AF, EF, and the tensile capacity all come from the manufacturer, or those ASTM minimums. And if this is not exposed to earth, we're going to use a 0.8. There's no bend, it's 1.0. So first step is we calculate our design value here. Again, we saw that equation earlier, 86.4 KSI. We can relate stress and strain. It's linear elastic, Hooke's law, you guys remember that. And we can calculate the strain value from Hooke's law. Then I can determine what the reinforcement ratio is. If this was steel, it would just be AS over BD. Here we have AF representing the area of the fiber. And the importance of calculating the reinforcement ratio that you're using in your design versus the reinforcement ratio of the balance condition is it tells us where that tipping point is between tension controlled and compression controlled of the masonry, right? So if I know what the balance condition is, right in the middle between those two failure modes, if I'm less than that, I know the bar is going to rupture. If I'm higher than that, then the masonry is going to crush. And so it's important that we calculate our reinforcement ratio and our balance condition. And in this case, it's less than the balance. So it's on that left side of the plot that I showed you earlier. And so we see that we're going to get a GFRP reinforcement failure. And then we can calculate where the neutral axis is. And then once we have that, we have everything we need to calculate our nominal moment capacity of the wall, which we do here. And again, whether it's concrete, whether it's masonry with steel, we're basically pretty familiar with this expression other than the 0.8 C sub B. Okay? And I would ask questions, but I know we don't have time right now. So just remember, 0.55 is the resistance factor because we're tension controlled. This case, it's designed for FRP rupture. Although remember what I said earlier, we'd probably actually prefer compression control because this value here would be larger and our element would carry more load that way, right? All right, and so this is the suggested steps in the design procedure. And I won't go into detail, but this is basically what we just walked through. Step 3, we were looking to see what type of failure mode it is, and then whether it was controlled by the masonry or the GFRP, and so forth. All right. This is going to transition me to the second part, and I'm going to pick up the pace on this a little bit because I don't want you guys all walking out on me, getting back to work. But I wanted to pick a couple of quick topics on the research side. And so I picked how durable are GFRP bars? So your question may be, oh, I see the C sub E factor. This worries me. It's going to deteriorate and fall apart. Well, probably not. The Boeing planes with carbon in it, they don't fall out of the sky regularly, right? Strengthening, and then just a couple of things on strengthening. So in the first topic, one of the questions was, we started putting this into, actually bridges were the first, back in the 1990s, late 1990s, and the 2000s. It's kind of ironic because the first specifications came in buildings, but the first applications were in bridges, you know, and you saw that that didn't come out till later. So we did a study where we went out and we looked at 11 bridges that were constructed mainly using GFRP in the decks. And they had been out there from 15 to 20 years, and we were interested, how well is this actually holding up? You know, because this is maybe an inhibitor to some design engineers using the material. And we selected bridges in different locations, so different environments, some drier than others, some get more heavy salts, more heavy winter locations. Two of these are actually in Rolla, Missouri, so if you come down for St. Pat's, you can always visit those. And we went out and we looked what information is out there on the durability. We only found one study by Professor Brahim Ben Mokrane up at Sherbrooke in Canada. And so out of the bridges we selected, we tried to fill in more gap of older structures where we sampled this material. And so these were the main things. I won't go into detail because you got them in your notes, but this is what we were trying to look for, is really basically how are they holding up, and are these C sub E factors we have in the standards realistic? They were all based on lab type durability studies, but the lab is not the real world, right? So we like real world temperatures, real world exposures. And just a cross section, you know, we looked at the temperature, the moisture. This is just a picture of the one of the bridges in Rolla. This is one of the bridges in West Texas, Amarillo. And I'm showing this one because this was one of the first bridges where we put FRP in the bridge deck. TxDOT was a little worried about, oh, I don't know if we want FRP in the entire cross section, so they put steel in the bottom mat and FRP in the top mat, you know, belt and suspenders, right? But here you can see we were taking samples, extracting cores, and the idea was to get samples of these bars that we could look at under the microscope or pull out that we could physically test in some different tests. This is one of the bridges in Virginia. You see all the markings in red. Well, since this is a non-metallic material, we couldn't take a rebar device to find exactly where the rebar was located. We're working on devices to find FRP bars in masonry or concrete or whatever, but some of our cores had nothing in them. Some of the other cores had more than one sample in it. But we developed a series of tests, and I'll show you just some quick pictures on these, but basically we were looking at the FRP as well as the concrete behavior over this 15 to 20 years. And we set this up as a round robin study. So we had University of Miami, my good friend Tony Nanny, who was at S&T or UMR, us, Penn State, and Owens Corning. And we wanted to make sure that the results we were getting made sense. So we did round robin where we had testing at least at 2 labs. And this shows you the test. This shows you some of the cool equipment we've got down in Rolla to do some of these tests. And this shows you some of the tests that we did on the concrete. Takeaway from the concrete, the pH levels in the concrete were where they'd be expected for the age of the structures. There wasn't a heck of a lot of carbonation, and the chlorides were pretty insignificant. So from the concrete side, it was doing great. From the FRP side, also doing pretty good. No signs of microstructure deterioration. So this figure on the left here, each of these dots is the fiber. When we zoom in, you can look at the fibers, see if there's cracks in it. You can look at the resin, which is the glue around the fibers, to see if there's any problems there. We also do EDS on the fiber, EDS on the resin. We can compare those imaging to pristine bars to see if there's anything that looks abnormal. Takeaway is it was performing really great. The other thing, when we did the Texas project, we put witness bars in the deck, and the witness bars could be cut out and removed so that we could do tensile testing on the bars. And if you look at this here, we saw after 17 years, 2.1% reduction in the tensile capacity. Now, we didn't have lots and lots of tests, and we don't have data at this point over lots and lots of years, but the framework of what we did in this study was supposed to set it up for us to collect more and more data. But if we do take 2.1%, we assume, hey, maybe this is somewhat of a linear relationship. That would mean after 100 years, it would only deteriorate by 12.5%. If I project out to the 0.7, remember the 0.7 C sub E factor, that would estimate a 239-year service life for this material. Now, there's a lot of assumptions, and you know what they say about making assumptions, but it's a piece of information that we'll learn more and more about. Now, I'm going to just wrap up a little bit quickly on reinforced masonry with steel that you may or may not want to repair with composites. So we had that standard I showed you a little bit earlier at ACI for unreinforced masonry, and we've done some testing on what if we want to reinforce masonry externally to add additional capacity for whatever the reason may be. Maybe it's for seismic upgrade, as you see here, for example. There's other reasons why we might need to apply strengthening. Design errors occasionally happen. We had a precaster. They forgot to put all the shear reinforcement in the stem of the double T, so we could apply external reinforcement to replace the shear reinforcement that they forgot to put in. You know, there's lots of reasons here. Overloading, change in use, I mentioned a little bit earlier. But there's basically two different types of repair techniques on the exterior walls. One is the near surface mounted. I showed you what's unique about this study is it had reinforcing materials, steel reinforcing, fully grouted. And thanks to our friends up here in St. Louis that helped us with some of these specimens. There's a new technique called FRCM, which is a fiber reinforced cementitious matrix. So most of the early composite materials, if I'm going to do NSM or externally bonded systems, I use an epoxy, basically a super glue, right, to glue it to the surface. Since then, the Italians were the first to develop this, but they said, hey, why don't we use like something that's cementitious, right? CMU is made with a cementitious material. Let's kind of keep the materials more compatible and the same. So we did look at FRCM, which is these two are fabrics. The one on the right uses an epoxy. The one in the middle uses a cementitious material. And this just shows you some of the steps, you know, grooving for the formation of the groove when you're using near surface mounting. And, you know, you can tape it to kind of keep it looking cleaner. So if it's a repair, you don't necessarily harm the aesthetics as much. That's one of the appealing things of near surface mounting. But we looked at both cementitious as the adhesive as well as epoxy, as you can see on the top and bottom respectively. And then in the externally bonded, we used the cementitious PBO fabric, and then we also used the epoxy to see if there's a difference in these systems. And we have done tests where we've used an airbag, for example, but these were all tested horizontally because they were reinforced masonry, fully grouted cells on the interior, and then we wanted to see how these repair materials perform. I'm just going to give you some takeaways. There's references to reports you can look up and papers if you really want to dive into it. But first of all, near surface mounted with epoxy in these bed joints, what's kind of the takeaway? Well, if I compare CFRP, the C is for CFRP, the G is for GFRP, we see the CFRP gives us higher capacity, than the GFRP. That's because it's 300 KSI, right, versus 100 KSI, so we would expect that. But we get more ductility, more deflection out of the GFRP, and it's much less expensive. You might say, how expensive is GFRP? Well, it's kind of gotten to the point now, there's been some bridges that have been done in Ohio to where it's the same cost as epoxy-coated steel. So black steel is still less expensive, but you know, if you look at the service life of the structure and some of these other needs of the project, it may make sense to use it. If I look at near surface mounted now where I put cementitious in the bed joints, we get less capacity. And this is because of the way it fails. It starts to slip in the groove. And so our takeaway is, okay, probably cementitious material in a near surface mounted application is not as good as using an epoxy, okay? And, you know, I won't read those other details. Now, if we switch to externally bonded with epoxy and the glass up here versus the carbon, what happens here? You get a lot better performance out of the glass, even though the material has a lower strength or tensile capacity. And that's because of the compatibility of the two materials. If we think about carbon, very, very high strength stiff, much stiffer than some of these other applications. And so from a compatibility standpoint, it actually makes more sense to use the lower strength, less expensive material when bonding to the surface. And the analogy I would use is if we look at concrete, and I'm batching up concrete. Here in Missouri, we use a lot of dolomitic limestone, right, as our aggregate source. I could pick a really, really hard, dense aggregate like a trap rock. And if I want to develop a high-strength concrete, maybe 15 KSI or something, that hard, dense aggregate that's stronger than a dolomitic limestone, you would think, oh, I can develop higher strength concrete. You can't. The materials aren't as compatible. It creates more stress concentrations, and hence the lower strength aggregate is actually better than the higher strength. And it's kind of a similar takeaway here, where the glass is better than the carbon, as you can see here. And then for the externally bonded, using this PBO fabric that you can see here, again, that is more effective with the PBO rather than a carbon sheet. Same concept there. The carbon sheet is stiffer, higher strength, and so you start to have debonding failure because of the discontinuity and the stiffnesses of the material. So I'm just going to wrap up now, and first I want to thank some of our students at Missouri S&T for the second part of the presentation, and then of course I mentioned Heather, Dick Bennett, who will be here not too long, from the University of Tennessee to do a presentation. My former sort of mentor, Tony Nanny, who's now at the University of Miami. He's actually the president of ACI right now. And of course, some of the good folks on the committees that developed and worked on some of these standards. If you want to learn more, dig in, search it on the internet. You can find some of these papers. And last but not least, I would love to thank, Nick isn't here, but thank you so much to our sponsors. And it's been my honor to be up here today. Thank you very much for your attention.